Now that we know that defining a linear transformation on a basis is enough information to determine everything about the linear transformation, let's see some examples of how we can use this idea to actually work directly with linear transformations just in terms of bases. So for our first example, let's take this linear transformation T, and it's from R3 to R2, and it's defined by this formula, defined by these three inputs and outputs. So here, since I'm defining this linear transformation just on the standard basis for R3, this does determine a linear transformation on all of R3, as we've seen. So using this linear transformation, let's find t of -2 for -3. So the idea of working with a linear transformation defined on a basis like this is to always get back to the basis that you know somehow. So what we would like to do is express this vector in terms of the basis, because then we'll be able to use these sort of known values on the standard basis. Of course, for the standard basis, writing a vector in terms of the standard basis is pretty straightforward. Right? You can just read off the coefficients, essentially. So -2 will serve as a coefficient for the first standard basis vector, and then 4 will serve as a coefficient for the second standard basis vector, and then -3 will serve as a coefficient for the last standard basis vector. Okay, and the idea here is now we can use the characteristic property of linear transformations to sort of move the linear transformation into the vectors, basically. So first kind of distribute, quote unquote, distribute the linear transformation, so like this on each piece. But then we can move constant scalar multiples outside of the linear transformation, and the result of that is -2 times the linear transformation applied to 1, 0, 0, plus 4 times the linear transformation t applied to 0, 1, 0, minus 3 times the linear transformation applied to 0, 0, 1. And right, these values here, this one, and this one, this is what we know about t. Indeed, those are the only things we know about t. So we can use what we know. So t of 1, 0, 0 is 3 minus 1. T of 0, 1, 0 is 1 minus 1. And then t of, oh, I need a minus 3 times t of 0, 0, 1 is 2, 2. And now we just need to do a little vector arithmetic. So let's see, -6 plus 4 is -2, minus another 6 is -8, I guess. And then +2 minus 4, so -2 minus 6 is -8 again. Okay, so now looking at where we started and where we ended up, we were finding t of -2, 4, 3. We expressed that vector in terms of the basis on which we know t. We used the characteristic property of the linear transformations to sort of move the transformation inside, and then we used the values that we know and did some vector arithmetic. All right. So this is how you can work with a linear transformation when you know it on. This is how you can compute the output of a linear transformation when it's defined on a basis. Let's look at this the other way around. For the same linear transformation, let's find a vector x so that t of the vector x is 12, 0. So this is kind of the other way around, right? On the first example, we knew the input, we were finding an output. This time we know an output, we're trying to find an input. Now the key idea here is that because we have this linear transformation defined on a basis for R3, we have a handy basis for R3, and in particular we can write x in terms of that basis. So x is some number x1 times 1, 0, 0 plus some number x2 times 0, 1, 0, the second basis vector, plus some number x3 times 0, 0, 1. Okay, and we want 12, what side do I want to write it on? Let me write it over here. So we want 12, 0 to be equal to t t of this whole thing. Right? The problem is we don't know what the coefficients are, x1, x2, x3. But if we could find x1, x2, and x3, well, then we could write this down and distribute the t, sort of, and get x1 times t of 1, 0, 0, plus x2 times t of 0, 1, 0, plus x3 times t of 0, 0, 1. Right? Well, again, these are the values of t that we know. So the first one is 3 minus 1. The second one is 1 minus 1. Oops, I need an x2 here. And then the third one is 2, 2. Now, if you look at this equation that we have now, this looks as if we are trying to write 12, 0 as a linear combination of these vectors. And we know how to do that, right? To do that, we can interpret this as saying we have a matrix 3 minus 1, 1 minus 1, 2, 2, times some unknowns, x1, x2, x3, and we want this to be equal to 12, 0. And how we can solve this is by writing the augmented matrix 3, 1, 2, 12, minus 1, minus 1, 2, 0. Right, this is augmented. And then row reducing. And when we row reduce, here's the result that we get. So how much room do I have? OK. This is the result that we get when we row reduce. Now we can interpret this in terms of x1, x2, and x3. So this is saying x1 is sorry, this is x1, this is for x2, this is for x3, this is the augmented column. So this is saying that x1 is 6 minus 2x3, x2 is minus 6 plus 4 times x3, and x3 is free. So actually it looks like there are lots of vectors x that will do what we want. To get one of them, we could really pick any value for x3. I guess we might as well pick 0. So let's take x3 to be 0, in which case we get 6 and minus 6. So now we found values for x1, x2, and x3. So now we can write x. X is x1, which is 6, times our first basis vector, which was 1, 0, 0, minus 6 times our second basis vector, 0, 1, 0, and then plus 0 times our third basis vector, 0, 0, 0, 0, 1. So this gives us 6 minus 6, 0 as our vector x. And again, there are lots of other possible vectors that would work, inputs for t that would produce this as an output. We could parameterize them all just by sort of writing t here, right? T here, and then putting these values in here. So this one in here, this one in here, and then t right here instead of 0, if we wanted to do that. All right, so these last two examples were examples where this linear transformation was defined not just on any old basis, but on the standard basis for R3. And that made things sort of especially straightforward. I don't know if all of this counts as straightforward, but it's sort of best case scenario since we use the standard basis. But remember, we could define a linear transformation on any basis. It isn't necessarily the standard basis. And that would change how this looks a little bit. So let's look at an example where we have a linear transformation defined on some other basis. So here's a linear transformation defined from R3 to R4, and it's defined by these three values here. And it's maybe not obvious, but these three vectors do form a basis for R3. So there's three of them. They also happen to be linearly independent, which you can check if you want. And three vectors in R3 are a basis for R3. Okay, so let's find S of 1, 2, 4. Well, just like so this is the scenario where we know the input and we want to find the output. Well, if you remember back to the previous example of this kind, the first thing that we did was we wrote this input vector. So we need to write this as a linear combination of the basis that we have, our basis for R3. Well, unlike in the case with the standard basis vectors, it is not obvious how 1, 2, 4 is a linear combination of the basis that we have here. So I guess to figure out how 1, 2, 4 is a linear combination of these three basis vectors, we have to do the usual thing of setting up a linear system where we have x1 times the first basis vector plus x2 times the second basis vector plus x3 times the third basis vector equals the vector we want, 1, 2, 4, and then solve this system. So you can fill in the values here. And again, we can solve this by reinterpreting it as a linear system whose augmented matrix is 1, 1, minus 1, and then this vector goes here, so that's -3, -2, 5, and then this vector goes here, like that, 5, 4, -6, and then augment with the vector we're trying to get, 1, 2, 4, and then row reduce this. Now I've row reduced ahead of time, so you don't have to watch me do it. That's what we get. Okay. So this is telling us that, x1, x2, x3, it's telling us that x1 is -2, x2 is 4, and x3 is 3. So that means that, coming back to this vector, this input vector 1, 2, 4 is -2 times our first input vector, 1, 1, -1, plus 4 times our second basis vector right here, -3, -2, 5, plus 3 times our third basis vector, this one here, 5, 4, -6. And now we can proceed as we did with the last example of this kind. Now we can use the characteristic property of linear transformations to sort of move the S inwards. So this is -2 times S of 1, 1, -1, plus 4 times S of -3, -2, 5, plus 3 times S of 5, 4, -6. And these values for S we know. The first one is, why did I have to choose an example that's so big? You'll see. First one is 1, -2, 3, -4, plus 4 times 0, 1, 0, -1, plus 3 times 4, 1, -1, 2, 0. And then we can do this vector arithmetic, right? I won't do this vector arithmetic, so figure out what these 4 values are, and that will tell us what S of 1, 2, 4 is. Just do all this vector arithmetic. All right. So again, this is the sort of situation where we know an input and we want to find an output. Now let's look at the other situation, which was when we know the output what we want from the linear transformation, and we want to find if there's an input that produces that output. So that's this sort of situation. Over here I just have, this is what defines S again, just so we have it handy. So I have it handy, I would forget it otherwise. So let's try to find a vector x, and this x is going to have to be in R3 since it's an input for S. So let's find a vector in R3 such that S of x is this, 6, -7, 8, 6. Well, we can proceed like we did in the previous example of this type, so I guess that was example 1b. We're looking for, since x is in R3, we can write it in terms of the basis, 1, 1, -1, plus x2 times minus 3 minus 2, 5. When I say we can, since it's in R3, we can write it in terms of the basis, I should say if it exists, it's in R3, and we can write it in terms of the basis. We don't actually know if there is any such vector x yet, but if there is such a vector, then we can write it like this. Okay, hit both sides of this with our linear transformation S. And on the right-hand side, use the characteristic property of linear transformations to move the linear transformation inside. We get x1 times, so this is going to turn into S of 1, 1 minus 1, which is over here 1 minus 2, 3, 4, plus x2 times S of minus 3 minus 2, 5, which is 0, 1, 0, minus 1, plus x3 times S of 5, 4, minus 6, which is 4, minus 1, 2, 0. We want this to be equal to the output, right? Where we want to arrange things so that this is equal to 6 minus 7, 8 minus 6. That's an 8. Okay, and then as usual, this is turned into a linear system. So to solve the linear system, we write our augmented matrix 1 minus 2, 3, 4, 0, 1, 0, minus 1, 4 minus 1, 2, 0, 6 minus 7, 8 minus 6. And this last column, that's the augmented column. And then we row reduce. When we row reduce, we get this. Okay, so this tells us that x1 is 2, x2 is minus 2, x3 is 1. And right, the x's were what we needed to know in order to write our vector, the vector we really wanted, x. So x is 2 times the first basis vector in R3, so 1, 1, minus 1, plus negative 2 times the second basis vector in R3, which was minus 3, minus 2, 5, plus the third basis vector in R3, which was 5, 4, minus 6. And again, right, to actually know what the vector x is, we need to do this vector arithmetic, but I'm not going to make you watch me do arithmetic. That's not exciting. Okay, so other than the little wrinkle of having to work with this different basis, this worked out very similarly to example 1b. All right. Because this linear transformation goes from R3 to R4, there's actually another possibility that we should think about, so let's look at one more example. Let's find a vector x such that S of x is 1, 2, 1, 2. So again, we're going to play the same game. X is going to be some linear combination of the basis vectors in R3. And our goal is to find what linear combination should it be. These basis vectors are 1, 1, minus 1, minus 3, minus 2, 5, 5, 4, minus 6. So I'm going to skip ahead a little bit because this is essentially, for now anyway, the same as the previous, very similar to the previous example. The only difference is that this vector that we're looking for is different to what it used to be. Right, so now we hit both sides with S. We rewrite, when S hits each of these vectors, we use the known output vectors and rewrite the resulting system, and we get 1, minus 2, 3, minus 4. Well, actually, let me write it out. So x1 times this plus x2 times the second output, 0, 1, 0, minus 1, plus x3 times the last output, 4, minus 1, 2, 0. And we want this to be equal to 1, 2, 1, 2. All right, so now we can, to solve this equation, we can write our augmented matrix 1, minus 2, 3, minus 4, 0, 1, 0, minus 1, 4, minus 1, 2, 0, and then the augmented column is 1, 2, 1, 2, and then row reduce. And when we row reduce this one, here's what we get. But if you look at this, this one has a row that is all zeros except in the augmented column where it's a 1. But when we get this for the row reduced form of an augmented matrix that represents a system, there aren't any solutions. So this has no solutions. Okay, so let's back up and interpret no solutions in terms of the original question. The original question was to find a vector such that s of x is 1, 2, 1, 2. Well, if there's no, what we just found is that there's no such x. Right, so there is no vector that s sends to 1, 2, 1, 2. That's what this is saying. So one way to interpret this is that this vector 1, 2, 1, 2 is not in the image of s. Right? So s was from R3 to R4. I'm going to sort of decrease the dimension of everything by 1 just so that I can draw some pictures. So it's as if the domain space for S was a small dimensional space, and we're putting it into a three-dimensional space, sorry, a higher dimensional space. So here, right here, this two-dimensional thing is sort of standing in for R3. This linear transformation puts it over in this higher dimensional space, but we were looking, the output vector we were looking for is just not in the subspace that is the image of this linear transformation. I shouldn't be using, yeah. It just isn't an output that is produced by this linear transformation, right? One sort of a way to picture what this linear transformation is doing, even though the dimensions are wrong, one way to picture what this linear transformation is doing is it's taking this line, say, to there, this line to there, which determines this plane over in the codomain space R4, and this vector is just not in this plane determined by what happens to all of those vectors, right? So this linear transformation, it misses this vector. That's what I'm trying to say here. This linear transformation hits a lot of stuff in R4, but this vector is not one of the things that it hits.